Good morning, students. Welcome to video lecture on microwave and optical fiber communication. Subject code U18EC709. Topic modes in optical fiber. Modes in optical fiber. The field configuration within the waveguide is referred to as mode. The mode of a fiber refers to the number of paths for the light rays within the cable. Depending on the refractive index profile, there exist three optical fiber configurations. One, single mode step index fiber. Two, multi-mode step index fiber used in application requiring distance of less than 1 kilometer. Third is multi-mode graded index fiber, mostly used for long distance communication. Types of fibers. Depending on the material composition of the core, there are two types of fibers are used commonly. They are step index fiber and graded index fiber. In step index fiber, the refractive index of core is uniform. In graded index fiber, the refractive index of core is not uniform and it is a function of radial distance from the center of the fiber. Once again, single mode fiber classified in step index fiber classified into uh, single mode and multi-mode. Graded index fiber classified into multi-mode fibers. The source for single mode fiber is laser and the source for multi-mode fiber is LED. Single mode step index fiber. Here you can observe the light propagation in single mode fiber is shown here. Single mode means uh, the fiber will permit only one mode to propagate and does not suffer from the mode delay differences. The mode delay difference will occur when n number of modes will propagate and receive at the receiving end at different time instants. But in case of single mode, there is no delay difference. Here, due to the small size, the interconnection of cables and interfacing with other sources is difficult in case of single mode fibers. Multi-mode step index fiber. You can observe the light propagation in multi-mode step index fiber. Here, these rays are meridional rays propagating through the axis of the fiber. Here, the light rays are propagated down the core in zigzag manner. The light ray follow many paths during their propagation. The transmission bandwidth is fairly small due to different optical lengths caused by various angles. Due to this limitation, multimode step index fiber is typically used in the application where it requires the distance of less than 1 kilometer. Multimode graded index fiber. Here, uh, n number of optical signal can be propagated through the core of graded index multimode fiber. The optical signal travel in helical path. You can observe the propagation path in multimode graded index fiber. And here it is mostly used for long distance communication. The key differences between single mode and multimode fibers. Here, single mode fiber, the core diameter is around 8 to 10 micrometer. In case of multimode, it is 50 to 100 micrometers. The source for single mode fiber is laser, and the source for multimode fiber is LED. As the dimension of the single mode fiber are very small, thus its handling and coupling is quite difficult when compared to multimode fiber. The next is the propagation of only a single light ray results in less attenuation in case of single mode fiber. However, due to multiple reflections of light rays, the attenuation is more in multimode fiber. A few more key differences. The next is the transmission distance of single mode fiber is nearly 50 times greater than that of multimode fiber. Single mode optical fibers are less expensive as compared to multimode optical fibers, but instruments associated with single mode optical fiber are makes it expensive as compared to optical multimode optical fiber. Uh, the transmission bandwidth of single mode fiber is high when compared to the transmission bandwidth of multimode fiber. Here, uh, the same points are tabulated. Once refer number of operating modes, core diameter, optical source, bandwidth, handling and coupling, optical signal to the fiber, initial cost of fiber, attenuation, transmission rate. Here, the attenuation is less and transmission rate is high in single mode fiber, whereas the attenuation is more and the transmission rate is less in multimode fiber. V number and number of modes in a fiber. Here, V number is also called normalized frequency. Here, V number determines the number of modes that can be accommodated by a fiber. It is given by V is equal to 2 pi A by lambda multiplied by numerical aperture. A is the radius of core, D is core diameter, lambda is the signal optical signal wavelength in nanometer. Here, the V number associated with the number of modes as if V less than or equal to 2.405, then the fiber is a single mode fiber. If it is greater than 2.405, then the fiber is a multimode fiber. For a step index fiber, the number of modes accommodated is given by m is equal to v square by 2. In case of graded index fiber, it is v square by 4. A sample problem on V number. Calculate the number of modes of an optical fiber having a diameter of 50 micrometer. N1 is equal to 1.48, N2 is equal to 1.46, lambda is equal to 820 nanometer. Here, you can simplify the problem like this. The diameter of core is 50 micrometer. Write down the data. The core refractive index is 1.48. The clotting refractive index is 1.46. Means here N1 is greater than N2. And the wavelength of the signal is equal to 820 nanometer. Means it is in first window. In second window, the wavelength is around 1300 nanometer, and in third window, the signal wavelength is around 1550 nanometer. Now here, you can directly substitute in the given formulas to determine the number of modes accommodated by the fiber. Here, the type of fiber is not mentioned, so in general you can consider it as step index fiber. You can substitute the formulas related to step index fiber. One more problem on V number. Refer to the solution. The procedure is same. By substituting in relevant formulas, you can determine the required parameter. Problem 3. Here, the core diameter is 80 micrometer. Index difference, it is delta. 1.5% means it is equal to 0.015. It is operating at 850 nanometer. It is the wavelength lambda. The core refractive index is 1.48. Determine the normalized frequency. For that, you require numerical aperture. Na is equal to n1 root 2 delta. Substitute in the formula. And once again, substitute in the formula of V number and number of modes accommodated by the fiber. Refer to the solution. One more problem on V number. A step index fiber with numerical aperture. Here the value of numerical aperture is given. It is the light coupling efficiency of the fiber. The value of numerical aperture is more, then the light coupling efficiency is more. Supports approximately 1000 modes. Here the value of m is given. The wavelength of the signal is 850 nanometer. What you have to determine? You have to determine the core diameter. You need to determine the value of d. Here the value of d, it is double the value of a. You can determine the value of diameter. Here a is pi unknown. Here it is d. I think it is pi d by lambda. The value of d is 64.49 micrometers. If it is radius, then you have to specify 2 pi a. Here if it is diameter, then pi d by lambda into Na. So it is d. Here in the next the second requirement, the wavelength is 1320 nanometer. In the third requirement, the wavelength is 1550 nanometer. By substituting the relevant parameters, you can determine the value required. Thank you. We will meet with the next lecture.